Welcome in, everyone. So, if you're a college student currently navigating the, let's be honest, sometimes overwhelming world of electrical engineering, I want you to just take a deep, relaxing breath. You're in the right place. In today's explainer, we're completely stripping away the complex jargon to look at something fundamental and, honestly, incredibly practical. We're talking about peak and RMS values. We're going to ground ourselves in how electricity actually behaves in the real world, so let's just make this simple. To start things off, I want to gently pose a question about something you probably look at, well, every single day. When you plug your phone or your laptop charger into the wall, you might notice a little label on the power brick that says 120 volts, or maybe 240 volts, depending on where you are in the world. But what does that number actually represent? Like, is there a constant, unwavering stream of exactly 120 volts just pushing into your device at all times? Honestly, don't worry at all if you aren't sure of the answer right away. By the end of our time together today, you're going to completely understand this, and you'll see why the reality is actually way more dynamic than just a single static number.
Section 1. Riding the AC wave.
Okay, let's dive right into this. Electricity coming from your wall is definitely not a flat, boring line. It's in this constant state of motion. It's actually a lot like the rhythmic rising and falling tides of the ocean. Now, looking at the equations and waveforms here, please don't let the Greek letters overwhelm you. Just calmly guide your eye strictly to the highest arching peaks of these waves. Those points, the ones labeled Vm for voltage and Im for current, well, that's our starting point. Everything else is literally just the journey to get up to those peaks and back down again.
I really want to reassure you that the terminology here is exactly what it sounds like. The peak value, or maximum value, is simply the absolute highest point of that electrical wave's rhythm. It's the moment of maximum effort. Think about if you're swinging on a swing set. The peak is that exact split second at the very highest point of your arc, right before you change direction. In an electrical circuit, it's the maximum voltage or current reached during one complete cycle. It's a super important number for sure, but as we'll see in a minute, it doesn't quite tell the whole story of how much work is actually getting done.
Section 2, the problem with averages. Now, what's really interesting about this part is you might be wondering, why don't we just find the simple average of this moving wave to figure out its power? You know, kind of like averaging out varying test scores to find your overall grade. Well, looking at the full cycle, notice how the wave arches beautifully into positive territory above the zero line, but then it dips down and spends an exact equal amount of time mirroring that shape in the negative space below. It pushes and then it pulls with the exact same intensity. Let's put this textbook truth into some everyday common sense terms. Because the wave is completely symmetrical over one full cycle, the mathematical average of a full sinusoidal current is, well, it's simply zero. Every single positive value in the first half of the cycle is perfectly canceled out by a matching negative value in the second half. It's exactly like if you step one pace forward, and then you step one pace backward. Your average change in position? Zero. If we relied on a simple mathematical average, our electrical equations would essentially tell us there is absolutely no power in the circuit at all. And this brings us to a really fascinating paradox. Think about it. If the simple average of the voltage and current is exactly zero, how is your laptop actually charging right now? How is your desk lamp emitting light? Clearly, energy is being transferred, right? Heat is being generated. Work is being done. It's a lot like rubbing your hands back and forth quickly. The average movement of your hands is zero, but the friction still makes them warm. The energy is very real, which means we desperately need a better mathematical tool than just a simple average to measure it. Section 3, enter root mean square, or RMS. So to solve this little paradox, we introduce the root mean square, or RMS. I want you to think of RMS not as some terrifying, complex formula to memorize, but really just as a helpful translator. It takes that complex, wavy, back and forth alternating current and translates it into a steady, direct current equivalent. As the simplified definition shows us, an alternating current delivers the exact same power to a resistance as a direct current equal to the RMS value. So if you have an AC circuit powering a heater and a DC circuit powering an identical heater side by side, the RMS value is simply the steady voltage you'd need to make both heaters exactly the same temperature. It is, in essence, the effective power. And this brilliantly illustrates exactly how we calculate that effective translator. If you just look past the integral calculus, down to the much simpler equation in the middle, you'll see it. The RMS value, whether we're talking about current or voltage, is simply the peak value, that Vm or Im from earlier, divided by the square root of 2. That's it. You really don't need to do complex calculus every time. You just use this elegant, simple relationship. Now, the square root of 2 is roughly 1.414,
And this single constant number is literally the magic key you need to unlock the whole problem. Whenever you know the soaring, absolute highest peak of an electrical wave, you just divide it by 1.414, and boom, you instantly have your practical, working, effective RMS value. So, going all the way back to our very first question, when your charger says 120 volts, that is the RMS value. The actual peak of the wave inside your wall is much higher. It's actually around 170 volts. Crazy, right? But effectively, it does the exact same work as 120 steady volts.
Section 4. A peaceful takeaway.
Let's move to our summary and see how this all builds together. You've navigated through the complex shifting waves and uncovered the magic of the RMS translator. So the crucial point is really just contained in these 4 simple truths. Number 1, alternating current electricity flows in moving waves. Number 2, the peak is simply the absolute highest point of that wave's push. Number 3, because the wave pulls back exactly as hard as it pushes forward, simple averages cancel out to 0. And finally, number 4, the root mean square, or RMS, is our translator. It turns that complex wave into a steady, workable equivalent that actually tells us how much power we have to use.
But before we wrap up, I want to conclude with a thought that ties this beautiful engineering concept right back to your everyday life. In AC circuits, the peak voltage is flashy, right? It's the highest number on the graph, but it's just a fleeting moment. The RMS value is slightly lower, but it represents the consistent, actual work getting done. In your demanding studies, please don't burn yourself out trying to operate at your absolute peak 100% of the time. It's just not sustainable. Instead, try to find your RMS, your steady, effective, workable rhythm. But it does make you wonder, if 120 volts is actually 170 volts in disguise, what other hidden, massive forces are quietly operating behind the simple numbers in your textbooks? Thank you so much for learning with me today. Take care.